There's a lot going on in this particular problem. If you look at the answers, you notice that we're talking about when is the function decreasing or increasing. We're also talking about when is the function concave down or concave up. Well, we've got exactly what we need to determine whether it's increasing or decreasing. We have the first derivative. We have the second derivative, and that will help us to determine whether it's concave up or concave down. So let's go take a look at the first derivative is equal to the natural log of x over x. For the whole problem, x is always positive. The denominator is positive here. We just have to focus on the natural log, and we know the natural log equals 0 at 1. And so therefore, when x is greater than 1, we're going to have a first derivative that is going to be positive, and that means that the function will increase. And so I can look straight away here and say, you know, a and b can't be right. It's increasing when x is greater than 1, and this interval of increase is not correct in e. So it leaves us with c and d as our possibilities. All we need to do now is look at concavity, and that's the second derivative. And the second derivative here says, geez, we've got 1 minus the natural log of x over x squared. We got a positive denominator again, because we know the x's are always positive. The numerator will equal 0 when the natural log of e, when e goes in for x, because the natural log of e, of course, is 1, and 1 minus 1 would give us 0 up top. So when x is greater than e, we're going to get a second derivative that's negative, and that means that the function will be concave down. Function will be concave down. So as I look to my choices here, I see the function is concave down when x is greater than e, so C must be my answer. This problem 27 has to do with the fundamental theorem of calculus, part 2, and it doesn't look exactly right. A right problem, a good-looking problem, would look like this. Any number not to 2x, but to just a single variable. I'm going to use u here, and this one would be very doable, because then we could say, well, the derivative then just is the square root of u squared minus u. And obviously, I've let u equal 2x. So in order to get the derivative with respect to x, I have to back substitute. And when I back substitute, I get not u squared, but the quantity 2x squared. And then I'm going to subtract the 2x. And, you know, I'm taking and evaluating the derivative of u, and then I have to multiply by the derivative of u, the chain rule, and u is 2x, so I've got to multiply by the 2 at the end. I got to multiply by the derivative of what our replacement was. And so now to find the derivative at 2, f prime 2 would be simply put in 2 times 2, and I get 4 squared minus 4 times 2. I get the square root of 16 minus 4 times 2. I get 2 square roots of 12. So looking at my options up above, I see E is the answer. Number 28 would have us know the derivative of the inverse sine, and there are 2 of them that we need to put to memory, and we haven't worked at what we have to have in our memories for the AP test. But the only 2 inverse trig functions that we need to know in terms of their derivatives are inverse sine and inverse tangent. They'll ask about one or the other. And so in this particular case, we're going to use this first form that comes right from the table, and we've let 5x go in place of u, so we'll say the derivative equals 1 over the square root of 1 minus, and our u is equal to 5x, And don't forget the chain rule. You need to multiply by the derivative of 5x, or 5. And so our final answer will be 5 over 1 square root of 1 minus 25x squared. So looking at my choices, it seems that E is the guy. We're shifting over now to part B of section 1. These problems may need a calculator, and 76, I believe, is one that needs a calculator. We're given velocity. We're asked about acceleration. We can certainly go off by hand and say, you know, the acceleration at t is equal to the derivative of velocity. And we've got a product here. So we're going to have to use the product rule. The first times the derivative of the second, and that would be 1 over t plus 2 times the derivative of the inside, which is just 1. Don't forget about that. Not really necessary here, but you might get into a situation where you need it. So it's the first times the derivative of the second plus the second times the derivative of the first, and the derivative of the first is 2t. So let's straighten that up a little bit and say, geez, the acceleration is equal to t squared over t plus 2 plus 2t times the natural log of t plus 2. Now we're asked to find the derivative at time 6, that is the acceleration, the derivative of velocity. So we've got 36 over 8 plus 2 times 6 is 12, natural log 8. And this is where I would go to the calculator, and right below here I've done that work ahead of time. And so 36 over 8 plus 12 times the natural log of 8 gives us that 29.453. And C is clearly the answer to this problem 76. 77, although it is in the calculator section, a calculator is not necessary or needed. What we need to recognize is some of our rules of integration here. The integral from 0 to 5 of 3 plus 2 f of x can be certainly written as the integral from 0 to 5 of 3 plus 2 times the integral from 0 to 5 of f of x. And this derivative, 0 to 5 of f of x, you can piece it up however you want. And so you've got some pieces here. 0 to 3 is 6. 3 to 5 is 4 more. The entire trip is 6 plus 4, or 10. We're supposed to multiply that by 2. We're supposed to integrate 3, and that would give us 3x with an upper and lower limit of 5 and 0. The upper limit would be 15. The lower limit would be 0. 15 minus 0 plus 20 is a total of 35. 35 is our answer. Therefore, D is the solution. No calculator needed.